Hello and welcome to Tech Simplified TV. Recently, we have discussed about interconnect or wire delay in the series based on interconnect in physical design. There are many other delays in VLSI. Do you know about them? Do you know their names and their source? In today's episode, we will discuss about different delays in VLSI. Stay tuned till the end of this video if you want to clear your concept about delays in VLSI. Now let's take a look at the pointers we are going to discuss in today's episode. First, cell or gate or propagation delay, first slide, and then cell or gate or propagation delay, second slide. Third, clock delay or latency. Fourth, more on clock latency. Fifth, transition delay. Next, what is clock skew? Different types of clock skew. Next, what is jitter? Various types of jitter, path and net delay. And finally, input, output and exit delay. Now let's move to the first slide. First slide is on cell or gate or propagation delay. Recently, we have completed a series on interconnect. While discussing that, we have mentioned about two types of delays. One is propagation or cell delay, or another is interconnect delay. So actually, signal transmission in a circuit is not an instantaneous process. It takes some time. That finite time is called delay, and delay has mostly two different components. First is gate delay, another is net delay or wire delay. In last series we have discussed about interconnect or wire delay, and today we will discuss about different types of delay. On that, this is the first one, that is cell or gate or propagation delay. That is basically time required in transmission of signal through the gate. This is the time required in transmission of the signal. If this is the gate, signal will travel from here, this point, to that point, and that will take some finite time. That is the basically cell delay. Next, signal transmission is not instantaneous, and there is a finite time gap between the signal applied at the input of the gate and response of the input found at output of the gate. That we have already mentioned, that signal transmission is not basically instantaneous, and there is finite time gap between the signal applied at the input of the gate and response of that input found at the output of the gate. So although we are applying signal here, or the switching in the input is happening here in time domain, it will reflect at the output pin after some time here. That is the difference. That is the time difference. That is the delay basically. And propagation delay for rising and falling edge are not same. So here at the input, this switching is from 0 to 1, that is a rising edge, and here it's 1 to 0, that is a falling edge. So obviously at the output, since it's a NOT gate, the response will be just opposite. Like when it at input it's 0 to 1, at output it will be 1 to 0, that is high to low, and that delay related to this high to low transition at the output is called TPHL, that is high to low delay, and in a similar manner it's called TPLH, and these two are not same. The propagation delay TP is defined as the average of TPLH and TPHL, and TP is equal to TPLH plus TPHL. So if that is the total waveform, total delay is basically summation of these two. So we are done with this slide. Now let's move to the next slide. Again, cell or gate or propagation delay. TPLH, that is response time of gate for low to high output transition while input switching from high to low. That is, input is switching from high to low, and that time output is transiting from low to high. That delay is called TPLH. Another one is TPHL, response time of gate for a high to low output transition while input switching from low to high. Input is switching from low to high and the output is from high to low. The delay is usually calculated at 50% point of input-output switching. Ideally, we assume the signal is rising just like that, a straight line. That means in time domain it's instantaneous. There is no time delay. From 0 to 1, this transition happen ideally if we take the waveform like that. Actually, it doesn't happen. It takes some finite time to reach its peak value. So when we calculate the delay, we always try to do it 50%. If that is the peak value and that is the minimum value, so in between that, just exactly between that is called 50%. And here also, while it was high and it's going down, so minimum just 50% of minimum to maximum, that's transition. So 50% to 50%. Here it's 50% of that output signal. So, and here is the 50% of the input signal. So that the difference between these two 50% is TPHL. Similarly, TPLH. The delay is usually calculated at 50% of input output switching. Rise time. Time it takes for leading edge of a pulse to rise from its minimum to maximum value. Rise time is typically measured from 10% to 9% of the value. So TR, this is the rising time. Time it takes for the leading edge of a pulse to rise from its minimum to maximum value. Rise time is typically measured from 10% to 90% of the value. This is the rise time. This is the 10% of, this is 10%, it is 90%. This is in between time, how much it takes to rise from 10% of the value to 90% of the value or magnitude. It's called rising time. Similarly, fall time, time it takes for falling edge of a pulse to fall from its maximum to its minimum value. Fall time is typically measured from 10% to 90% of the value. So we are done with this slide. Now let's move to the next slide. Now clock delay or latency. Clock latency or clock insertion delay. So clock delay, clock latency, clock insertion delay all point to the same thing. Defined as the amount of time taken by the clock signal in traveling from its source to the sink. In a system, there are flip-flops or time-dependent or sequential components. To operate sequential components properly, we need clock signal. So clock signal is also another signal. In real world, it takes some time to travel from one point to another. Clock-dependent or clock-driven flip-flops, they are called sync. If that is the clock source, obviously it will get connected with some flip-flop, and these are the flip-flops. So basically this is the path the signal, clock signal would traverse from clock source to flip-flop A, and that is the path for flip-flop B. So this is the clock latency. This the time it requires to cover this finite path is the clock latency or clock insertion delay, defined as the amount of time taken by the clock signal in traveling from its source to the sinks. Next, clock latency comprises of two components. One is clock source latency, another is clock network latency. Now let's see what are those two things. Clock latency is basically summation of source latency and network latency. Clock source latency or source insertion delay is defined as the time taken by the clock signal to reach the clock definition point from clock source. If that is the clock source like PLL oscillator or some other source from external clock source, when the signal is entering the design, there is a point where it's defined as the clock definition point. This is the clock definition point, but this is not the origin of the clock. Origin of the clock signal is clock source. So from clock source to this definition point, it's a finite distance and the signal takes finite time to travel. That is source latency, clock source latency. And from there, within this network, the signal takes some time to travel. That is network latency. This clock source latency also known as source insertion delay, and clock network latency or network insertion delay is defined as the time taken by the clock signal in traversing from clock definition point to the sink. Clock definition point to the sink is network latency, and from clock source to clock definition point is source latency. We are done with this slide. Now let's move to the next slide. More on clock latency. Now this is another diagram where the same thing is repeated for generated clock. So a generated clock, this is a system with generated clock. A generated clock is derived from master clock. A master clock is a clock defined using the create clock specification, and when a new clock is generated in a design that is based on master clock, the new clock can be defined as generated clock. That is the master clock. If the generated clock is going inside the network or the circuit or the design, so that is the point we have defined as the clock definition point. So from clock source to clock divider is used to generate this generated clock. So from clock source to definition point is basically source latency, and from there to the sink path, that is network latency. Pre-CTS latency and post-CTS latency, that is also defined in VLSI. Latency is the summation of source latency and network latency, as we have said. Now pre-CTS estimated latency is considered, because pre-CTS we consider the estimated latency and during the synthesis, and after that propagated latency is considered. So we are done with this slide. Now let's move to the next slide. Transition delay. This is the diagram. Defined as the time taken to change the state of the signal. That is, this is the minimum value, this is the maximum value. In digital, we say this is a 0 and this is 1. So, the 0 to 1 transition, it's taking some time, that finite time. Again, from 1 to 0 also, it's taking some time. That is transition time for a signal. Time taken for transition from logic 0 to 1 or 1 to 0, expressed as rate of change of logic or the speed of transition, how fast it's changing its logic state, that is rate of change of the logic or the speed of the transition. Also termed as Skew and measured in volt per nanosecond. Rise time is defined as the time taken for signal to reach from low threshold voltage to high threshold voltage. Fall time is defined as the time taken for a signal to reach from high threshold voltage to low threshold voltage. Fall time is defined as the time taken for a signal to reach from high threshold voltage to low threshold. And both rise and fall time measured in absolute value or percent. Low and high thresholds are fixed voltage levels around the mid volt. So that is the mid value, that is 50%, and low and high threshold voltage are measured around this. Threshold voltages can either be 10% and 90% respectively or 20% and 80%. These are two commonly used convention of measuring low and high threshold voltage. Either it's 10% is the low and 90% is the higher threshold, or 20% is the lower threshold and 80% is the higher threshold. The percent levels are converted to absolute voltage levels at time of measurement by calculating percentage from difference between starting voltage level and final settled voltage level. First, we express it in percentage, and while doing the calculation, what we do with respect to V minimum and V maximum, we measure or we express these threshold voltages. We are done with this slide. Now let's move to the next slide. Now clock skew. Clock skew is defined as the difference of insertion delays of two flops belonging to the same clock domain. Every component adds some delay in signal transition. Clock signal take finite time to travel from one point to another. So there is time difference between arrival of clock signal to two different flip-flops. Difference between arrival of clock of two flip-flops is skew. There are two types of skew, local skew and global skew. If this is the clock, common clock, and then it's getting divided. Here it's for flip-flop 1, then flip-flop to 2, and then flip-flop 3. So signal doesn't reach all these flip-flop at the same time, although they belong to the same clock domain. So there is a difference in time because it's a signal and a real signal is traveling through a real system. So it will take some time. So clock skew is defined as the difference of insertion delays of two flops. Insertion delay means the time taken in clock signal to travel from clock source to the sync point. So that's a first sync point, it's another sync point, it's another sync point. From definition point, that flip-flop 1, the network delay due to network latency basically is different. Network latency for this one is different, for this one is different. So the skew, the delay or the skew became different for all the flip-flop. And skew value can be positive or negative. So here we are showing positive skews only, not negative. So there are two types of skew value, positive skew value and negative skew value. So let's see what are they. We are done with this slide, and now let's move to the next slide. So different types of clock skew. Two types of skew depending on position of clock. One is local skew, another is global skew. This is the diagram. This is the clock. Now the clock signal is getting divided in two parts here. This is flip-flop 1, then combinational circuit, then flip-flop 2, then flip-flop 3. Here also some other flip-flops. So this is the shortest path. As we can see, signal will travel from this clock to finally reach here, and when signal is coming in this point and this point, there is a finite difference, that is local skew, FF2 minus FF1. Similarly, FF3 minus FF2, FF4 minus FF3, these are local. Now this is the longest clock path, and here also in this segment also there are local skews. And when we consider the global skew, that is longest clock path minus shortest clock path, the time taken in reaching the clock signal from here to here and from here to here, that is the global skew. So local skew is the difference of insertion delays of two communicating flops of same clock domain. Two communicating flops in the same clock domain, local skew is defined as the difference of insertion delays between two communicating flops. In the same clock domain. Global skew is the difference between the delay times for earliest clock reaching the flip-flop and latest clock reaching the flip-flop for a same clock domain. Now positive and negative. If the capture flop receives clock signal later than the launch flop, then it results in positive. This is the launch flop, this is the capture flop. It's receiving the clock signal later. So this is positive skew basically. And if the launch flip flop receives clock signal late than the capture flop, then all negative. This is the launch flip flop, the capture flip flop. The launch flip flop is basically getting the clock signal late. So the capture flip flop is getting the clock signal earlier, that is negative skew. So we know now there are 4 different types of clock skew. One is local skew, another one is global skew, and another 2 are positive and negative skew. So we are done with this slide. Now jitter. Jitter is another type of delay. Clock jitter is defined as the deviation of clock edge from its ideal position in time. It's like uncertainty. This is the ideal clock edge should be like that and might deviate from its position in both sides in time axis. That is the jitter. Clock jitter is uncertainty in the clock edge. When this clock edge will come or the position, clock jitter is basically the uncertainty in the clock edge, as we can see. The cause may be noise, a fluctuating power source, or interference from nearby circuit. There could be many reasons. Jitter is very much present in circuits. Now, jitter can occur in both direction, positive and negative. In both direction, we can see that uncertainty is in both direction. This clock edge might come earlier, this clock edge might come later. So, in both the direction. Can be modeled by adding uncertainty regions around the rising and falling edges of the clock waveform. Clock jitter can be cycle to cycle, period jitter and long-term jitter. There are different types of jitter also. So one is cycle to cycle jitter, another is period jitter, another is long-term jitter. These are common jitters. So we are done with this slide and now let's move to the next slide. Now let's know about various jitter. Now, cycle to cycle jitter signifies the change in clock period across 2 consecutive cycles. This is a clock signal. So, a complete cycle, it's 15 nanosecond and another clock cycle is like that, it's 18 nanosecond. So, any 2 consecutive cycles like T2 and T1 are successive clock periods, then cycle to cycle jitter would be T2 minus T1. And now, period jitter is difference between ideal clock period and actual clock period measured with respect to ideal clock period. So, if the ideal clock period is 15 nanoseconds. So for this clock period, jitter is 0. We consider T0 as ideal and that is 15. So actually there is no jitter in this clock period. Although here there is a jitter, so it will be 3 nanoseconds. Right, T1 minus T0 because this is the ideal and period jitter is measured with respect to ideal clock period. So ideal clock period is 15 and T1 is 15. So there is no jitter. Ideal clock period is 15. T2 is 18. So there is a jitter of 3 nanoseconds. This is the calculation. Now long-term jitter. Long-term jitter is the deviation of clock edge from its ideal position for a clock with period 20 nanosecond. Ideally clock edges should arrive at 20 nanosecond, 40 nanosecond, 60 nanosecond, etc. If nth edge comes other than 20 into n nanosecond, there is long-term jitter for nth edge and that is equal to 20 multiplied by n minus 200. And half period jitter is the measure of maximum change in clock's output transition from its ideal position during 1/2 of period. It's calculated for half of the period, not the total period. We are done with this slide. Now let's move to the next slide. Now path and net delay. Path delay. Delay assigned to paths from each input to each output. The minimum time required for a signal from an input pin to propagate through combinational logic and appear at the external output pin, also known as pin-to-pin delay. The time taken in signal traveling to this path, that is the delay. It's a combinational logic and no clock is involved here. So that time, how long it takes for a signal to travel from this input to output, that is measured as pin-to-pin delay or path delay. Now net or wear delay. This net or wear delay is basically interconnect delay. We have already discussed in a series. The difference between time a signal is first applied to the net and the time it reaches to other devices connected to that net. That is basically a net delay or wear delay. It is due to the finite resistance, capacitance and inductance of the net. Instead of our devices, because of its size, inductance effect is also there. So we try to represent this net as a combination of resistance, inductance and capacitance, and these are basically parasitics of the wear, we know, and many delay models are there to calculate this delay. We have already discussed those delay models and done their calculations in previous series. So this is basically the net delay or wear delay. We already know. We are done with this slide. Now let's move to the next slide. Input, output and exit delay. Input delay is the time at which the data arrives at the input pin of the block from external circuit with respect to the reference clock. So from outside world, this is the system. This is the input pin from where it's going to within that system. So the time required from that external point to this point, this is the arrival time of the signal, that is the input delay. Next is output delay. Output delay is the time required by the external circuit before which the data has to arrive at the output pin of the block with respect to reference clock. From this system, the signal, it's leaving from this point and going this output point. This is the output time or output delay. That time required go to that point. This is the basically output delay. And exit delay is, it is defined as the delay in the longest path or the critical path between clock pad input and an output. It determines the maximum operating frequency of the design. This is the longest path, and the delay in that longest path or the critical path is basically exit delay. So three delays: input delay, output delay and exit delay. So we are done with this slide. And actually we are done with this episode, so we will conclude here. Thank you for watching up to this point. Don't forget to like, share and subscribe. If you have a question or query, please put it as a comment. If you have a dislike, also put it as a comment. Thank you again and bye for today.